Buenas tardes a todos. Gracias por tomarse el tiempo de participar en este espacio. Con este webinar retomamos los webinars de la Comisión de Exploración y Desarrollo del IAPG que iniciamos el año pasado y que vamos a continuar este. Los webinars serán casi todos los jueves de este año a las 16 horas. Se componen de 5 ciclos diferentes: últimos descubrimientos exploratorios de la Argentina, magmatismo y sistemas petroleros, exploración offshore, microsísmica y exploración de reservorios shale en Argentina. Como verán, son temas muy interesantes y variados. Esa es la idea de los webinars, que tienen como lema compartir experiencias, ampliar las miradas. Queremos crear un canal que permita la difusión y el intercambio de conocimientos, con un enfoque multidisciplinario. Es así que pretendemos que funcione como un medio de comunicación eficaz entre colegas de las diferentes disciplinas que integran las geociencias, sin olvidar a todos aquellos de profesiones afines de la industria. Hoy comenzamos con el ciclo Microsísmica y Sísmica Pasiva. Tenemos el agrado de contar con la presentación del Dr. Peter Duncan, de la compañía Microseismic. Él desarrollará el trabajo titulado Microseismic Vadis. En nombre de la Comisión de Exploración y Desarrollo del IAPG, quiero agradecerle al orador su excelente predisposición para participar de este evento y por el tiempo y el esfuerzo que ha dedicado a preparar su exposición. La presentación en sí tendrá una duración aproximada de 45 minutos. Al término de la misma, dispondremos de un intervalo de tiempo para responder preguntas y abrir el debate. Las preguntas o comentarios pueden ser formuladas por escrito en el panel del chat a la derecha de la pantalla. Durante cualquier momento de la presentación, aunque las mismas serán contestadas al final por el Dr. Peter Duncan. Las preguntas pueden ser tanto en inglés como en castellano. Esperamos que esta contribución les resulte enriquecedora y que la disfruten. La charla entonces está a cargo del Dr. Peter Duncan de la empresa Microseismic, que nos presentará, como dije, Microseismic Vadis. Bienvenido, Peter. Voy a presentarle un pequeño currículum porque tiene una vida muy larga dentro de la geofísica, así que él me pasó unas pequeñas líneas para que les diga. Peter Duncan es presidente y CEO de Microseismic Incorporated. Posee un doctorado en geofísica de la Universidad de Toronto. Peter fue presidente de la SEG, de la SEG, Sociedad de los Geofísicos de Exploración, en el periodo 2003-2004. Es miembro honorario de las asociaciones profesionales SEG, CISEG, que es la SEG canadiense, GSH, Sociedad de Geofísica de Houston, y de la EAGE, que es la Asociación Europea de Geofísicos e Ingenieros. Ha ganado además la medalla de oro Virgil Kaufman de la SEG en 2014. Es actualmente presidente de la GSH, la Sociedad de Geofísicos de Houston. Dicho esto, lo dejamos con la presentación de Peter. So, please, Peter, go ahead with your presentation.
Thank you very much, Luis, and thank you to the organizing committee for inviting me to Argentina today. Argentina is one of my favorite countries to visit. I just wish I weren't visiting virtually instead of being there in person. Having to sit here and look at this silly glass eye in front of me rather than looking into your smiling faces is really a disappointment. It's a lot more difficult, I find, than speaking to a live audience. On the other hand, I should say that doing it from Houston is probably really good for my cholesterol count, because every time I go to Argentina, I'm afraid I eat way too much of your wonderful meat. The committee and Luis asked me if I would come and give some reminiscences about my experience with microseismic, where it's been, where it is, where I might see it going in the future. And so I thought about that, and I asked Luis how long I would have to speak. And he said, oh, we have an hour and a half, but perhaps 45 or 50 minutes. And I said, but Luis, this has been my life for the last 20 years, and it's not really all that exciting. I can probably do this within 15 or 20 minutes. He said, no, Peter, we want you to take a little longer than that and put some meat on the bone. So I will try. What I am going to do today is talk a little bit about the science that I got introduced to, in 2000, 2001. This idea of passive seismic, where we were listening to the sounds of the earth passively, and from that trying to tell something about our exploitation of the reservoir. A science that eventually went to become critical to the development of the oil field, particularly the shale gases and oils in North America and around the world, that went through a very exciting period of being the new kid on the block, of being the new technology for all of us, and then perhaps now has become a commodity. And it is interesting that within the space of 10 years, something could go from being new and exciting to now considered, well, I don't want to say passé, but perhaps at least something that is well understood and mature in the science. So I will attempt to review that history and then leave you with a bit of a vision of where I think the technology and the business is headed in the next few years. Making predictions is always dangerous, but that's what Luis asked me to do, and I will make some attempt. So if we talk about the history, I first want to say that a really lovely book written by Vladimir Grechka, the late, unfortunately, Vladimir Grechka, and Werner Hegel, came out a couple of years ago at the SEG. And the beginning of the book gives a rather nice history from their perspective of the microseismic technology. I'm going to review it a bit here, but the price of the book is really worth just this section on history. I have to say that some of the other chapters in the book, I don't agree with everything they said. If you've read the book, you'll know what I'm talking about. And some of the chapters, the mathematics are a little bit, well, certainly over my head, and you might expect that from Vladimir. But the book is a great book and a wonderful addition to the literature on microseismic monitoring. The history, we begin, I think everyone knows that microseismic technology, passive seismic technology grew out of classical seismology, the location of earthquakes and using the signal, the passage of the signal, the recording of the time of the arrival of the signal, to know something about the structure of the earth. We've re-engineered that down to the oil field in order to use some of that classical technique today. The first real application or early applications of this passive seismic, in fact, is in the mining business, where seismometers were deployed for safety reasons, largely to predict rock bursts. And that remains a very active technology today in most of the mines of the world, where they continue to practice mine safety through microseismic. In the 60s and 70s, the injection of waste product, and at the beginning a lot of this was military-based, waste product into the earth, studying where that waste product was going became a microseismic application. And I think the watershed moment in this was the earthquakes that occurred around Denver in the middle 1960s as a result of injection of waste product at the Rocky Mountain Arsenal. And that observation of the correlation between the injection and the earthquakes that occurred led Chevron and the USGS to do some marvelous studies on the Rangeley oil field in Colorado in the early 1970s, where they related the movement of the pressure front to the induced seismicity. That kicked off, I think, a lot of different microseismic applications, geothermal applications as early as the 1970s around Fenton Hill, where they had an intrusion that they were fracking to make a heat exchanger for geothermal units, and that work has continued. The hot dry rock experiments, largely in Europe in the 80s and 90s, the work continues today in that field. And sort of simultaneously, for oil and gas applications, the Sandia National Labs and the DOE became involved in a number of studies. First, surface microseismic applications. I was surprised to learn this as early as 1973, 1974, involving El Paso in the Green River Basin and the San Juan Basin. Probably not too successful, for they then started to concentrate more on downhole with Amoco in the Wattenberg field in the late 70s. And the really the momentous work that was done at the Rulison field, what became the MWX well site, then revitalized as the M site tests, a lot of publications, Norm Warpinski heavily involved in those, that moved forward the understanding of how microseismic can illuminate what's happening in the oil field, and culminating probably in the very important work that was done by UPRC, well, a consortium that was led by UPRC in the Cotton Valley, a lot of papers by Jim Rutledge and others that came out in the late 1990s associated with the work done there. Again, multi-well experiments that really gave some insight as to how powerful the technique can be to watching the development of an oil field. And then finally, the commercial aspect, as the shale gale took off, maybe beginning 2003, 2004, what had been largely a research and academic experiment to that point became really necessary to the early development of the shale fields. And I think since then, within the shales, there have been perhaps more than 200,000 frac stages that have been monitored. Probably still a small fraction of the total number of frac stages that have been executed, but a significant number nevertheless. So if we follow that shale gale, I wanted to try to put this into perspective. And so I actually, as a proxy for frac monitoring, did a little chart of the revenue that Microseismic Inc. has had since 2003. And this is largely, I think, very correlable with the number of stages that were fracked, or the number of revenues in the fracking commercial side of the business over that same period of time. And you can see that in the early days, as the shales were newly being developed, there was a lot of excitement. And maybe we thought that Microseismic had crossed the chasm as the number of wells went up and peaked perhaps at 40,000 stages per year. And I think there were some estimates that the microseismic business at that peak in 2012 might have been a $400 million a year enterprise market size. But then after 2012, we witnessed, along with the rest of the oil business really, a decline in revenues and activity. And now, of course, we had the price effects here early that then really collapsed in the 2016 era. I know all of you have experienced that. But then even beyond that, we continued to see a decrease in microseismic. Now, some of that microseismic use, some of that was perhaps oil price uncertainty. But what we heard from our clients, what I heard from people just in the market in general, in the world in general, was that microseismic technology in general was too expensive given the economics of the oil field in those days, and that the production activities, the amount of oil and gas they were getting from the wells was good enough. Why spend a penny more on science if what I'm getting from my wells meets the expectation of my manager or my board? And in reality, what was going on was a macro change to the oil and gas business, where the oil and gas business, the E&P business, was changing from a value industry to a growth industry, from one where the industry was rewarded for replacing or even increasing reserves, finding more oil and gas, to one where it was the return to the investors on their investment, where it was putting money in the hands of their investors, that became more important than finding new oil and gas reserves. That changed the dynamic of the oil and gas industry, and I think has been responsible for what happened to the service business in general and the microseismic business in particular. So now, with that sort of context of the history, I want to progress to talk a little bit about how the industry responded, both to that growth and then that decline in utilization over the past few years. And I could have titled the talk really this: better, faster, cheaper, but the three-legged stool that the service business, and it's not just the oil and gas service business, it's any service business, the three-legged stool that we sit on, the legs are doing things better, doing things faster, and doing things cheaper. And as we go through, from my perspective, the microseismic industry over the last 20 years, I think we can characterize almost all the changes that have developed as being driven by trying to be better, and certainly in times of increasing use and in times of increased money available for the technology, getting better technically is the theme there. Getting faster, though, that's kind of a better. And in fact, the definition of better is really important. We'll talk more about that. But getting faster to put the results in somebody's hands faster is an important stool in this, or an important leg in this three-legged stool. But at the end of the day, cheaper is always in the minds of our clients, in the minds of the people who are consuming our product. And when that red arrow starts heading down to the right, cheaper becomes perhaps the most important of the characteristics that we're looking at. So, being a geophysicist and thinking chronologically, I'm going to look at this better, chapter, faster, cheaper, this past, present, future, look at it first in terms of acquisition, then in terms of data analysis, the normal chronological way that we approach our field work. So in the beginning was downhole. I mentioned how El Paso had tried back in 73, 74 to do microseismic monitoring of fracking from the surface, and they found that the signals were too small to be captured on individual phones, so they did the natural thing. They went downhole and captured the PNS waves close to the reservoir by putting the microphone close to the noise source. And in the early days, it was vertical wells with perhaps 6 or 7 levels. I think they started off with as few as 3 levels in the well. The wells would be placed close, the monitor wells would be placed close to the wells that were going to be fracked. When I say close, usually 300 or 400 feet, maybe 1,000 feet away. Maybe 30 to 50 meters or as high as 100 meters away, the phones being placed at reservoir depth. And an improvement that was made quickly over the next few years was to go from 6 levels to as many as 99 levels, or perhaps even more, getting a wider aperture to get more fold and to get more move-out difference so that you could more properly locate the events. And the other development that happened was to do things in real time. So better, more stations downhole, faster. Get the answers into the hands of the clients in real time so that they might know, A, that their experiment is working, and B, what they could be doing differently. So moving from vertical wells to horizontal wells in the industry, a development that was made by the oil and gas, by our clients, to try to do their recovery from the shales faster, to get more intersection with the reservoir, led to a problem with downhole microseismic in that you started to have the completion points being farther and farther away, exceeding the distance over which you could sound with downhole, and adding more downholes, more monitor wells to approach these long laterals got to be expensive. So you had to do it cheaper, and the change, the adaptation to this was to start to use tractoring in the horizontal wells to move the geophones along in a parallel horizontal well, parallel to the well that you're completing, to be able to keep the geophones close to your completion points. So again, still doing it in real time. The next thing, I think the future, or where we are sort of getting to now, and if I want to predict the future, is to actually improve even beyond the 99 level. And in fact, tractoring in, we had to back off on the number of channels that we could still sound. The way to improve that appears to me to be using DAS, or digital acoustic sensing. The fiber And I don't really think the fiber on the outside of the Wellbore, it's too expensive and you lose it too often. I think it's this intervention fiber where you can put it down the Wellbore in a monitor well, that is going to offer the opportunity to approach infinite sampling. You can have spacing between the phones or the observation points that are on the length of a meter or less, and you can have it over the entire length of the well. And so now you have really good sampling of your data. Now fiber has a problem in that it's a single component, and that means we have to find other ways to approach that problem. And also fiber has a problem in that there's so much data that needs to be processed that it challenges being able to do it in real time. So there are issues of faster and cheaper that are still issues with fiber, but it certainly appears to be a better solution, particularly if we do what has happened in the downhole and go more and more to multi-well so that we can achieve a better imaging and a more complete imaging of the focal mechanism of the events. So the history from a single well with a few channels through to multi-channels to horizontal wells so that we can keep the or tractoring into horizontal wells so that we can keep the geophones within the capture distance of the signal, to sampling at an almost unrestricted amount with a digital acoustic sensor over in the future. That seems to me to be the progression of where we've gone with downhole, and all the time doing it in real time. Now, an advance, I believe, in the technology over downhole, or in response to some of the issues with downhole, was to move to the surface, to try to solve those problems that El Paso had back in 73 or 74. And what drove going to the surface in the early days was that in the Haynesville, where it was hot, the geophones placed down at the reservoir were burning up. We were losing equipment. It was becoming expensive. So the idea was, could we put phones on the surface that would then be able to sense downhole? And we found that we could do, but to overcome it, we had to put a lot more phones than perhaps El Paso did back in 1973, 74. The next thing that drove the use of surface arrays was this idea that the laterals that were being drilled were becoming longer and longer. And tractoring into the well was expensive. Tractoring into the well also put the wellbore at risk. And so the idea of being able to monitor from the surface might make it faster and cheaper in the long run. And it turned out there was a better aspect to it as well, in that with a large surface array, you could get a bigger sample of the focal sphere, the wavefront, from the events in the subsurface, allowing you to do a better technical imaging of the events in the subsurface. So there was better, faster, and cheaper aspects to this move to the surface. In the beginning, we used autonomous nodes. You see a picture of a survey that I did in 2005 or 6 with these autonomous nodes. We tried various configurations in the field, initially looking at rectilinear or crossline, inlines and crosslines of geophones, found that didn't work very well. And we tried 3C phones as well, thinking that we could get shear waves and P waves. Here we ran into some of the similar problems that El Paso had, in that the single phone point, the single sensor point, was not a very good way of recovering the signal. There was some advantage to having groups on the surface, and that the shear waves were getting absorbed by the near surface, so we weren't getting very large signals. So what happened is we developed in order to do it better, we had to move to multi-channel, almost small 3D systems with lots of cables and geophones and 6 to 12 phones per group laid out over miles or many square kilometers, and anywhere between 1,000 to 3,000, even sometimes 4,000 channels being sensed at once. And in order to do it in real time, the autonomous nodes were not up to to getting the signal back from that many channels in real time, so we had to use wired systems. We did respond to the cost aspect of this by using 1C phones rather than 3C phones. The 3C phones weren't really working for us anyway. And but we did have to go to multi-phone groups building antennas on the surface in order to suppress the noise. All of that drove the expense up. And while it was reasonably cheap on a well-by-well basis for a multi-well pad, for an individual well, particularly vertical, not particularly cost-effective. So we needed to drive the cost out of the system. Better? Perhaps yes. Faster? Well, as fast. Cheaper? Not so. And that's where we got into doing buried arrays. And in fact, one of the first times we tried one of these buried arrays was in the Haynesville, where the client said, I really like what you've done in terms of a surface array, but I can't afford to be laying out all these phones on the surface. And we knew that if we could put the phones away from the free surface of the earth, it would reduce the noise, capture more signal, and perhaps then we'd be able to still get the better part of it, still get as good a technical solution, but at a lower cost. So the buried array came about as a response really to a cost issue. We put in a few phones, perhaps 1/10 the number of stations that we had for a straight on surface array. We could go back to using 3C phones because being deeper, we now got rid of the overburden problem and we could start to capture the shear waves, although I will confess that over time we haven't found that much use for the shear waves. The P waves have been sufficient to give the imaging we needed. And we could radio these individual stations, which are now as much as a kilometer apart. We don't want to wire them together, but communications by cell phone, Wi-Fi at first, and now cell phone, that's the way the future has gone. That allows us to still be able to use this sparse array over sometimes several hundred square kilometers to be able to collect that data in real time and still be able to be fast in terms of giving the information to the client. So again, better, perhaps not. These are designed to give the same quality of results as surface arrays, faster, same speed with radio communications, cheaper, absolutely, as long as you are doing a large number of wells. Buried array doesn't work for a single well because this drilling in of geophones is quite expensive. But we found that if you were going to do more than 3 to 6 wells, that using this buried array approach was really the cheapest way to go. So again, acquisition largely driven by the whole idea over time of getting better with the technology, faster with the delivery to the client, and cheaper. Now let's move to an analysis and see how the analysis of the data that we're acquiring has changed over the years and benefited from the money in the glory days when we were moving between 2003 and 12, and then continued on as we've tried to respond to the downturn in the market. Well, the initial stage of what we had to do, and this is no different than classical seismology, was just to locate the events. And of course, the original idea driven by classical seismology is that with as few as a single receiver, with as little as a single receiver, if we could capture the P and S arrivals, we would have 2 observations of the arrival time of the signal, which we could difference to give us some estimate of how far away the event was. And if we had a 3-component phone so that we could get the tilt of the wave field, we could point that distance back towards the event location in order to locate the event. Of course, we need 2 observations, so if we couldn't get the S wave, or even if we didn't want to, we could have 2 receivers that would both see the same event, and if we could measure the difference in arrival time of the event at the 2 receivers, we could also back predict where the event had occurred. Now, this is no different than, say, lighthouses on the banks of the La Plata River, where you're trying to find a boat and you have 2 independent observations of the boat and you just draw your arcs and you know where it is. So the key here, though, is in terms of the development of the technology, is that there are really two ways that we can estimate this arrival time difference, either of the two phases or of the signal at many different stations. One, and the original one, the one that comes from classical seismology, is to pick the arrival of these different phases or the arrival at the different geophone locations, the different stations. And when I say pick, we could use the machine, but generally speaking, it is done by hand, and we use the experience of the interpreter to pick the P and the S arrival time from the wave field, and then we throw away the waveform and essentially find the location in the earth where these spikes, the picks, line up. In other words, to state it more properly, we migrate these spikes to find the location of the source. It's really just a migration. Well, an advance to this was, rather than pick, let's use the classical migration approach that we have in conventional seismic, reflection seismic, and migrate the waveforms and use the statistics of the whole wavelet, and find the point where the whole wavelet aligns, at least statistically the best, where it stacks up, to then say that is the arrival time difference, or in fact where the event is located. Now that has been a move. We have moved largely away from picking the events and then throwing away the waveform to doing full waveform imaging and doing it in real time. It gets rid of some of the subjective bias, and as long as we have enough stations, whether downhole or surface, this is a better way, not necessarily cheaper, but a better way to go in terms of doing the imaging. Well, once you've got those locations, how has the technology evolved in terms of handling the data? Well, we started off with just estimating the hypocenters and displaying them. And this, in the old days, some of these plots were pretty cartoonish. They got more sophisticated, and largely, though, what we were looking at is static displays of the hypocenter estimates relative to the wellbore, the treatment well, in map view or section view, where we could size the different spheres by the magnitude of the event, let's say, and color them by the different stages so that we could see the progression down the well. And from these, we could estimate the frac height, the frac length, or even make estimates of the stimulated reservoir volume, which then we could compare one treatment to the next to say what was better. Now, better here is a really interesting discussion. What makes the stimulated reservoir volume better? Is it the density, the complexity within that volume? Or is it the size? Or is it better if it's restricted to the reservoir? Well, an interesting discussion that we've been having since diagrams or displays like this began. And I think we've eventually come to a solution, but let's talk about that as we go forward. Now, beyond the static displays, we started to go into dynamic displays where we could now make a story about what was really happening as we fracked the well. Now, here is a display. Some of you will recognize this. This is from the marvelous work that Carolina Crovetto and the rest of the crew at Pan American did, where they had a well in the Nukian Basin. And there had been a previous well, a parent well, if you like, over here, the blue line, that had been on production for several months before they started fracking these two wells that were further to the east. And you can see as the frack progressed from the toe at the bottom of the screen towards the heel, that when it aligned with the fractures that had been established by the previous well, we had a total change in the character of the fracking that was going on, even though the frack parameters didn't change all that much. What a marvelous vision, what a marvelous view in real time, well, it could have been in real time, of how the rocks, the reservoir, were responding to the in situ properties of the reservoir and what had been done to the reservoir in the past. So moving from static to dynamic, I think, was a huge increase in our understanding of what's going on in the subsurface. Of course, we still really needed to do that in real time. And if I can get my slide to advance here, there we are. I want to talk just a little bit then about how we've gone from simply these dots in the box, whether they're static in real time, to some of the modern analysis techniques that we're using today. So we started off, as I said, with dots in the box, but a marvelous realization was that each one of these dots, each one of these little earthquakes, these microseismic events, had a focal mechanism. There was a sense of motion in the earth that created this noise. And that if we could capture that and invert for it to come up with the focal mechanism of the event, then we could now create a better geological model of what was going on in the subsurface in terms of failure planes. A discrete fracture network is one realization of that, which could be upscaled to a new idea of a stimulated reservoir volume with distributed permeabilities. However, not however, but immediately we said, well, if we're doing that, wouldn't it be better if instead of just looking at the stimulated reservoir volume, we could run reservoir simulations to predict production? That might be a better tool or a better number to give to our clients. Well, we had to first figure out what part of that stimulated reservoir volume was propped and what part was unpropped, but we developed ways to approach that issue and end up with reservoir models that started to be useful, started to be realistic, that we could history match with the production. Sort of as lagniappe, along at the same time, we began to realize that these focal mechanisms that we determined also were very revealing of the stress in the reservoir at the time of failure, how that stress changed as we stimulated the reservoir. That affects the production, but also had implications for wellbore stability. So now we've got how much production is coming out, what are the stresses. All of that we felt needed to be upgraded to real time. Now going from dots in the box in real time to these more difficult models of reservoir production in real time was a challenge, but in fact we overcame that in the last few years. I say we, I'm not talking about just Microseismic Inc., I'm talking about our entire community, and started to be able to deliver to the engineers some idea of the stimulated reservoir volume and the amount of production that they could get in real time as they were producing the well. Well, why were we doing that? Well, the reservoir engineers had begun to find, as they produced more wells, as they began to drill their wells, infill wells, closer and closer, that there was a certain amount of interference going on between the wells, that the production that they were getting out of any individual well was being affected by the wells next door. Some great work by the Shell folks in the Permian Basin was showing that as they looked at the number of wells, the well spacing, if you like, they've taken the number of wells in wells per section, wells per square mile, as that number of wells increased, that the production on a per well basis actually decreased. So now it says, well, what should the optimal well spacing be to achieve the most hydrocarbons? And so that's where we needed to start to deliver as a better product in real time how much the production was going to be affected by adjacent wells. However, there is an issue here that soon came to light, and that it isn't just the amount of hydrocarbons that are coming out of the ground, but whether or not that increase in hydrocarbons as you change the well spacing was economic. Now, you remember I said the business had gone from a growth business to a value business where the return on investment became important. And this is when we began as a community, as an industry, to realize that we had to justify that drilling that extra well to get those more hydrocarbons actually had a positive economic impact. So here's an example of where we had a 4-well per section development, and we wanted to test a 6-well section per development, a 6-well per section development. And we found that going to 6 wells, we increased the amount of hydrocarbons by 43%, almost the same ratio as the number of wells. But the increase, because of the increase in costs and maintenance charges, created a net present value of 28%. And in fact, if we went to 8 wells per section, the amount of hydrocarbons was not sufficient to pay for the extra wells. And of course, back to this same shell work, this is a price-sensitive calculation. So at $80 a barrel, we could find that we might be able to use this many, and they removed the horizontal axes here, but this is more wells per section, and you can see that at an $80 you could afford more wells than you can at 50 wells. Beyond that, the increasing price of drilling and the increasing price of operations offsets the increase in hydrocarbons to the point where you are no longer paying for it. An important observation, and interestingly enough, when that observation became public, some severe corrections happened in the marketplace. In July of 2019, we saw this drop that made the Wall Street Journal, this drop in Concho's resources in their stock value. This happened with Shell, with Exxon, with Chevron, with a lot of them in that period where the red arrow was going down to the right, where the realization was that every one of these shale wells that were being drilled were not necessarily all going to produce the same amount as the very first well that you put into that reservoir, that there was some competition between the wells for hydrocarbons, and that the costs might override the return on investment. What's going on here? Well, as an industry, as we tried to explain it, we came up with the term frac hits or production interference, or as Ali Denishy says, he wants to call this fracture-driven interactions, that there is an interaction that has to be recognized between the wells. Well, a marvelous paper by the QEP groups explained what these fracture-driven interactions are quite simply, and that as we drill as we drill a parent well and we frack it and we begin to produce it, we draw down the pressure and create a pressure sink such that when we put a child well nearby it, the treatment tends to flow into that pressure sink, and it will compromise the stimulated reservoir volume that we are creating in that child well, and that it will affect the production of that parent well. Now, not only will the treatment be drawn to the pressure sink, but we will also, as we have created that production, we will have robbed some of the production that could be had by these child wells. The kinds of things we saw from these fracture-driven interactions as we began to recognize that this was going on, we saw sometimes a temporary loss of production, sometimes a permanent loss of production, poor SRV development around the child well as modeled by reservoir simulators or maybe 4D seismic. And at the end of the day, something that became even more and is becoming even more important, wellbore damage, getting stuck in the wells, in the child wells, where there has been damage done by the production, or getting stuck in the subsequent child wells by damage being done to wells that have been drilled before or during the stimulation of adjacent wells, and really even loss of the wells. We've experienced in some cases where one operator we were working for lost 6 out of 8 adjacent wells in 2 pads in the kind of failure that you're seeing here on the right-hand side. In the Eagle Ford, for example, and here is an example of what's going on, as they've drilled more and more wells nearby, they have increased the reservoir pressure to the point that they are stimulating some of the pre-existing strike slip faults in the area, which then go in and hit the nearby wellbores, causing wellbore damage and in some cases loss of the wells. What we see here, the blue events are dip slip, small magnitude, small area of failure wells that are kind of the meat and potatoes of increasing the stimulated reservoir volume. The red strike slip faults, when we see an increase in the amount of that activity, then now we know that we are in danger of having the adjacent wells become damaged. And in fact, this is becoming more and more of why people are monitoring wells. And when they see those strike slip faults being activated, by backing off on the rate of injection, by backing off on the pressure and the slurry rate in their stimulations, they are shutting down this strike slip failure and saving the wells. And that's an important idea towards what might be a possible future for microseismic monitoring. Now, Mike, we know that as shales have been developed, there has been a tendency to test a few stages and then say, well, now I understand the formula and I am just going to treat that entire well the same way. This goes against your geologic and your engineering intuition. I know it does, because that identical treatment does not account for the variation in the geology, and it does not account for what's going to happen as a result of adjacent wells or mechanical issues or the kind of fracture-driven interactions that we are seeing. Indeed, this pump and pray technology leads to what we've seen in the oil field, in the shales, over the last little while, 5 to 10% average recoveries. Frac hits that kill parent wells, maybe temporarily, maybe permanently, maybe cut them off. Child wells that underperform, leading to a loss in reserves that you can claim. Cluster and well spacing that's too large and too close. Well, either if it's too large, the well spacing, you perhaps are leaving hydrocarbons behind. Too close, and you're killing the economics of your play. And perhaps as much as 20% of your completed wells accounting for 80% of your production. Not the way to get promoted. So could we do better? What might be possible? One of the things we've said, if you could monitor somehow, if you could make each one of these stages perform identically, and to do that, of course, you're going to have to monitor in real time, but if you could watch how that stage is performing, how it's changed because of the geology, as a result of the geology from the stages before, then maybe you could make it more ideal in its completion. So we tested this. We took a real well. We took one of the stages that wasn't as good as the best stage, the ideal stage, and we made each one of those stages identical to that. Very little additional cost in terms of the treatment. All we did was change the effective treatment length in our modeling, the effective treatment time in our modeling by a few minutes, perhaps an hour more or less. And what we found was that with very little increase in cost, we increased the reserves returned from that well by 65.5%. Well, you might say, wait, the results that people are getting from the wells, we already have been told that they're good enough. But if you could get 65% more hydrocarbons for nearly the same cost, I don't think anybody would turn that down. But it does require real-time monitoring of your wells, which maybe is the future of microseismic. It would require probably that we monitor a large percentage of our wells. It would require probably that we go to this buried array approach or some permanent monitoring approach in order to keep the costs down. But it would allow us to adjust, since we're doing it in real time, on the fly. It would allow us to try to match every stage to a real-time template. If we can do that SRV modeling in real time, we would now judge better, not by stimulated reservoir volume or even by hydrocarbons that would be produced, but rather by the return on investment, by doing the economic calculation in real time. Would pumping for an extra half hour, would that produce that extra amount of hydrocarbons that would pay for that treatment and then cause an increase in the return on investment over time? And it would allow for a real-time, for the real-world geology and changes in the real-world geology as you move down the Wellbore. And I think most importantly, at least this is what we're seeing today, it would allow for the mitigation of FDIs. There is nothing worse than losing a Wellbore to a company who have invested $5 to $10 million in the Wellbore And if we can, by monitoring and by adjustment of the treatment in real time, save that well, then we've more than paid for the microseismic monitoring. So, and you've seen this before, I know because I've shown it before, but I really still believe that if we can cook every stage just right by monitoring every treatment or the majority of the treatments, that we've really achieved the objective of doing something better, faster, and cheaper for our clients through microseismic monitoring. Now, is this going to happen? My last slide, where I'm going to finally get to that point where I ask or answer the question, where are you going, microseismic monitoring? And so I've taken the curve before that showed the growth in microseismic monitoring through the heyday between 2005 and 2012, and our experience since then, fighting the price of oil, fighting the change in the market, the change in the industry, from being one where we were rewarded for simply finding hydrocarbons at any cost to having to find hydrocarbons at a price that would make money. I've asked what's going to happen in the future, and I don't think that we're going to see this heyday, this $400 million industry again in the future. I think that new fields and FDI mitigation, the control of the fracking to not cause damage to the adjacent wells, that will cause a slow and measured increase in the amount of microseismic that's practiced over the next 5 years. I think that gets us back up close to maybe a $100 million business from where we are today. I think that there is the idea, and it's growing in our industry, of environment, safety, and governance, that ISM monitoring, social responsibility, the need to keep our license to practice, that seems to be becoming more and more important to the industry right now. And I think that has the opportunity of driving induced seismicity monitoring and driving more business towards our sector, frac monitoring and injection monitoring for that matter, which I still class as part of our microseismic monitoring. And then maybe one other thing that will come to play a little bit more in the future, I don't see it really kicking in for another couple of years, is geothermal. Geothermal, creating enhanced geothermal systems. Those are, I guess it's EGS, so I could easily confuse it with ESG, but enhanced geothermal systems where we are fracking the plutons in order to make heat exchangers. That is a fracking business, and there's a lot that industry, the geothermal industry, can learn from the oil business. And I think that there's an opportunity there as we begin fracking those batholiths to monitor. But again, I don't see that taking off for a couple of years. And even in this, what I think is a positive attitude, I'm a kind of a glass half full person, but even in that, I don't see our industry, the microseismic monitoring industry, getting to much more than maybe a $200 million industry in the next 5 years. So that's my comments. Where I've been, where I think we are, what's driven us, and maybe what will happen in the next 5 years to the technology as we go forward. And with that, I'd be happy to answer questions.
Bueno, Peter, muchísimas gracias por su excelente presentación. Thank you very much, Peter, for your excellent presentation. Por favor, vayan haciendo sus preguntas por el chat. Ya vemos que algunas están entrando. Mientras tanto, yo le pensaba preguntar to Peter, it is possible to record microseismic in conventional reservoirs? O sea, ¿se puede y es útil registrar microsísmica en reservorios convencionales?
So the answer is yes. Of course, we know that somewhere between 80 and 85%, maybe more, of the reservoirs, conventional or shale, are fracked. Fracking's been going on for a long time. What we find is what you have is a signal to noise problem for the most part. This isn't rocket science. The ability to detect signals has to do with how big are the signals when they're created, and what happens to them between where they're created and where you record them, and what is the noise environment where you're recording. In conventional reservoirs, we find that for the most part, the signals are smaller. Usually the pumping pressures and pumping rates are smaller than they are with shales. The amount of confining pressure or the failure pressure is less. So the signals start off being smaller. And often if you're in less consolidated, say in an offshore pile of sand kind of environment, you have more absorption of the signal. And then if you're trying to do this from the surface, you're in a noisy environment. I think in the near term, conventional or microseismic monitoring in conventional reservoirs is probably going to be in the domain of doing it downhole. And but the answer is yes.
Okay, so I have here a question from Efren Munoz. He says, thanks, Peter, excellent presentation. Does your projection consider refrac operation? And for that matter, what's your opinion on them? Can we recover some hydrocarbon from older completions?
So the answer is yes, and we've been exposed to doing refrac work, and it has been successful in the sense it's been technically successful in the sense of being able to recover microseismic information, of being able to characterize how the refracts went. But what we have found so far is that the additional hydrocarbons in general have not been sufficient to create a return on investment, a return on the cost of the refrac, such that people have been pursuing it very well. So while there was a flurry of interest in refracts, I'd say 5 or 6 years ago, since 2012, with the decrease in prices, I've seen less and less interest in doing refracts, and consequently less application of our technology to that endeavor.
Okay. I have other one from Natalie Requena. What type of microseismic array do you recommend to estimate frac height? Do you recommend other technologies that can be used together with microseismic monitoring to reduce uncertainty in the estimation, tilt meters or other technology?
So I think tilt meters certainly have their application. Again, you have to weigh the better, faster, cheaper. Typically, you're not getting tilt metered in real time. Typically, tilt meters are not necessarily cheap, and particularly if they're close to the surface, they don't see down, at least in my experience, they don't see down effectively below 5,000 or 6,000 feet below, say, 2,000 meters. So that's an issue. If you go downhole with tilt meters, that's great, and you do get a sense of frac height. But again, you have this issue of how much can you observe. Downhole microseismic is unquestionably better at seeing frac height than surface. I think some of the pressure applications have some opportunity to see frac height. Electromagnetic techniques so far don't seem to be very well adapted to seeing frac height. So I think a combination probably of surface for cost and downhole for frac height is the way to go to get frac height as well as good coverage on your well and a good understanding of focal mechanisms.
Okay, thank you. Eduardo Corti, he asked you the minimum magnitude detected by borehole microseismic in Barnett Shale is around minus 3.2. What's the minimum magnitude detected in surface microseismic for the similar conditions?
So we have seen, well, this is a question of signal to noise, and geophysicists know that you overcome problems by putting out more fold. So I would tell you that generally speaking, from an economic point of view, because that is the limiter, that we tend to see about 1/2 an order of magnitude less or higher than you do in the same environment downhole. I don't think you can say that with a downhole microseismic, you are always going to see down to a -3.2. You may be too far from the treatment and consequently limited by the horizontal absorption. But typically, if we have an ideal or a good quality downhole microseismic, and let's say it sees -3.2, then a good quality, economically affordable surface would see -2.7 as a rule of thumb.
Okay. Soledad Lagos, she asks you, she says, first, Peter, thank you for your talk. What do you think are the main challenges for a larger implementation of buried array monitoring in Argentina?
Sorry, for the application of what kind of arrays?
Buried.
Buried arrays. Yes.
Yeah, sorry.
No. I apologize. You see, I should be able to speak to you in Spanish, and then I would know. So, buried arrays. It's always the impediment is perceived cost. The impediment is that the costs on a buried array are front-loaded. It's the cost of the drilling in, and people are not sure that they are going to use the array enough to pay for it. You typically, like I've looked at the average cost of microseismic monitoring for all of the stages that Microseismic Inc. has done, and it's been about $10,000 per stage. But the downhole or the surface stages have been more close to $20,000 a stage, whereas buried array stages, where with a single buried array, we've sometimes done as many as 200 wells, more typically 30 to 40 wells, that gets the cost per stage for monitoring down to $2,500 to $5,000 per stage. So if you can make the commitment to monitoring a lot of wells, the cost goes down. But management always sees the $1 million to put that buried array in the first place. They see that as a risk that might not be recovered, and that is the biggest impediment.
Okay, another question from Roberto Andino. He says, thank you, Peter, for your excellent presentation. How important do you consider the velocity modeling in the microseismic, and what do you see in the future on this respect?
Sure. The velocity modeling is always important, particularly as you try to get finer and finer resolution of the locations of the events. We find that velocity modeling is particularly important in our downhole observations, where our arrays, and as they become longer and longer, those arrays are crossing between different horizons, different geological intervals. And those different geological intervals have different velocity properties, not just their velocity, but their anisotropy as well. And if you don't properly account for the changes in velocity in these different horizons that you are crossing with your array, then you end up with issues and improper location of your events. Vladimir Grechka's last book on anisotropy in microseismic addresses this a great deal. On the surface, we do use anisotropy, and we do need to know the velocity model, but we can calibrate it. And since we're looking more at average velocity over a much longer path, the velocity is a little bit less touchy. Our results are a little bit less sensitive to the velocity model. Still advocate doing the velocity modeling well, but a little less sensitive. You ask what's going to happen in the future? Frankly, I think the improvements that we're making now in location are small and probably sub-economic in the current environment. I don't think I'd be spending a whole lot of time on improving the location of the events right now.
Okay. Eduardo Corti asked, let me see, I think it's a bit upward. Okay, I will do the next one and then we go back. Neptali asked you in general, how different are focal mechanism estimation from multi-well monitoring when are compared with surface monitoring? What's the minimum number of wells to have a good estimation of focal mechanism?
So I think some work that was done by Ted Urbanchek and the ESG guys a number of years ago showed that for multi-well, for downhole monitoring, you really need to have at least 3 wells, and it's not just for focal mechanism, but also to see the location unambiguously. Now that was for 3 wells that were a typical aperture. If you can get a longer aperture, you may be able to do a little better, but still in terms of, if you look at the focal sphere, you really want to be able to see the changes in the focal sphere sufficiently to unambiguously get the focal mechanism. If you can get the P and the S waves and be able to do the simultaneous inversion of those for the mechanism, then I think 3 is enough. On the surface, we have a really good estimate of the focal sphere. We only use the P waves, but we get a pretty unambiguous solution for the focal mechanism. And by the way, it's not just nice that we get a solution for the focal mechanism. You do have to have a pretty good estimate of the focal mechanism with the surface arrays in order to put the locations of the events in the right place. That was something we learned early on. With downhole and where you're picking and throwing away and you're just using arrival time, if that's the way you're doing it, then you can actually get locations pretty accurately without focal mechanism. So I prefer the focal mechanism estimates from the surface because you have a more complete estimate of the focal sphere. And I would refer you to some of the work by Dave Eaton up at the University of Calgary to really talk about how complete an estimate of the focal sphere you need in order to get a good solution.
Okay, thank you. There's another one from Eduardo Corti. He asked, is there any way to evaluate the EPV?
Sorry, the which?
EPV?
Oh, is that the initial production volume? You mean the IP?
Yeah. No.
No.
No. I know in Spanish. Maybe Eduardo, can you write in English? What is?
So it's I. Is it E is I? Initial? P?
No, not the initial. It's okay. Let's go another one and then we go back.
What is it in Spanish, Luis?
Volumen apuntalado.
The volume at the point of loading? What's lado?
Apuntalado is no, I don't know. I don't know in English. And the explanation apuntalado in English is quite difficult for me because I don't know the word. Maybe someone can help us. Acá, propped volume.
The proppant volume. Yeah. Yes. So we know the proppant volume that goes into the well. What we really want to know is the proppant distribution. How has the proppant proceeded out into the completion? The way we have been doing it, it's one approach, has been to use a material balance approach. We know about what volume has been pumped, and we know about what volume of frac has been created by looking at the discrete fracture network, using the magnitudes of the events that we've seen to talk about the size of the fracs that have been created. So we do this material balance where we put the volume of proppant, we stuff it into the discrete fracture network for a particular stage, and when we run out of volume, we stop. And typically we find that that means about 15 to as much as 40% of the discrete fracture network that we create gets propped. There have been other attempts to do it with doped proppant that you could maybe measure from the surface with an electromagnetic technique. That's been tried a couple of times, and I don't think it's been very successful. And so I don't know of a better way to look for proppant distribution than this sort of, albeit simplistic, but at least based in physics model.
Okay, I had a lot of help here in the chat. Thank you to 20 people. So I have another one very interesting. Have you recorded microseismic in inverse regime stress? I mean reverse.
Yes.
Has sense to do microseismic in this type of regime?
Absolutely. And in fact, I didn't mention it, but when we talk about wellbore failure scenarios, the Eagleford is not a compressive environment, but there are pre-existing strike-slip faults that get reactivated as we pressure up the horizon. When you get into a reverse stress or a reverse faulting environment, there is a lot of active today tectonic stress that is tending to compress the wells, and when we lubricate those, we end up with failure. We did a number of wells in China, in the Sichuan Basin, which is a compressive environment, and we were shearing off a large fraction of the wells to the extent that they actually shut down operations, and the major oil company that was our client withdrew because of that. In the Nukian Basin, where you're over, as you get closer to the Andes, you are in more and more of a compressive environment, and we see some of the same kinds of effects. And it is really in these environments that using the focal mechanisms to get a handle on the existing stress, the stress at the point of failure, at the time of failure, that using that kind of analysis has been most effective in helping the operator avoid having wellbore damage.
Okay. Well, Peter, I think we are done for today. Very interesting presentation, very good answers to the questions. It was very clear. So I will switch to Spanish right now to finish
Sure. May I say thank you very much to everyone for their attention.
Of course, thank you. Bueno, muchísimas gracias. Estamos cerrando y terminando la sesión de hoy. Nuevamente quiero agradecer a nuestro expositor Peter Duncan por su tiempo y calidad de la presentación. Me gustaría agradecer especialmente a todos ustedes, los asistentes, que se pudieron unir a este evento y por supuesto los que participaron con sus preguntas. Fueron para mí muy interesantes y por supuesto motivadoras. También quiero reconocer a la gente del IAPG que hizo posible la charla con Alejandra Castro y Adriana Divito, y a Fede Spat de IPF que estuvo participando en organizar junto conmigo esta jornada. Bueno, antes de despedirnos les comentamos que la próxima sesión de este ciclo de conferencias 2021 será el jueves 20 de mayo, del ciclo Magmatismo y Sistemas Petroleros, que tratará sobre el tema Cuenca Cretácica del Norte Argentino y sus reservorios volcánicos asociados, el caso de Palmar Largo. Sus oradores serán Gustavo Bergani, de la Universidad Nacional de La Plata, e Iván Petrinovic, de SICTerra. La moderadora será Marta D'Angiola, de Weatherford. Bueno, muy buenas tardes a todos y muchas gracias por ser parte de este ciclo.